Here we go.
Happy Halloween.
Actually, we should do that.
All right. Here we go. Physics.
Not make crack jokes.
Get rid of the
Did
jokes.
Sam make crack jokes? Crack, no joke.
Yes.
I don't have Velveeta with
Brad,
me.
let me try to find a crack joke.
I'll find it. You find us a crack joke while I work on this doorknob question.
Yeah, work on the doorknob question. Don't worry about crack jokes.
Is this how to lock your parents in?
This is a Sam move.
Door does not.
Oh, I have to watch Calvin on the news.
Oh, because you're Sam.
Yeah, because I'm Sam.
Make sure to turn the volume all the way.
Hey, Calvin, where do I find this?
Put it up here too. It's on
Alright, I'm looking at Calvin on the news.
It's true.
Okay, tell your neighbor.
But not necessarily. It could be up
Magnet thingy.
It
Yeah.
could be up into the right.
No, it isn't.
Oh, it's not back there. The charger, yeah. Magnetizer. Yeah.
I see it.
Oh, yeah. Nice. I was going down below.
Thanks.
Welcome.
That's the answer. None of my business.
Oh,
the door.
I
will go to the
I will go to the gym just on Friday. You know, as long as it's after school. I have a birthday party.
During school.
No,
We're gonna say you'll have to.
I have a birthday party to go to, so you can't make it too late. I have to dress up
It
as
has to be
Scooby-Doo.
something along. No, we don't know the point.
That's not a joke. That's just for
What are you
fun.
doing?
All right. What do you say? D. Okay. Then the net force has to be 0 in the x and the y direction. So this has an x component, so this also has to have an x component to cancel it out. And there needs to be a y component because this is bigger than that. Okay.
I wonder which part of it is it? This might be the hair.
Okay, next question.
I might just have this one, and I'll go buy a different one. I don't want this one. Yeah, I know. That's why I don't want it. Fun way to get out here. I'm kidding, Brad.
I'm sure it's the worst place.
I can read the board. I can read the board. One eye.
You were in it. Let's test it.
Oh, those are forks.
Brad, do you understand the question?
I do understand the question.
I can see normally.
Oh, that's. Can we not go
Oh,
on?
Brett, yours is. No, Brett says like so strong. Okay. I like.
This is how we do
Yeah.
Thanks, Brad.
I saw something.
You call me Brad, right? Certain people call me Brad. I don't keep it like that.
I switch.
Sam always calls me Bradley. Everyone else calls me Brad.
The rest of the choir calls you.
Correct answer is,
B.
here we go, B. Okay, center of mass of the stick is at 50. Therefore, here's where the fulcrum needs to be, at 25.
We can't see your mouse, so.
Good call, thank you. Center of mass is at, man, I can't see my mouse now. Is at 50. Therefore, they're equal masses. Okay, next.
Physics.
Oh yeah. Where are you? Parking lot?
Tell your neighbor and tell them why. Don't just tell them intuitively.
I'm learning.
Give them a physics reason.
Ali said I can't leave.
Can't leave.
Okay, let's think about.
Where are you?
Let's do the funny
So
thing.
I-
You said
here's
that
my
you
reason
did
why.
funny, because that usually-
Here's my reason why.
So,
Okay, so the
far
force
away.
distributed from the ladder on the wall is a force area.
Tell them go check in.
On the wall of the ladder. So the hand,
I
as
mean,
it
we
extends, the
As it
ladder
goes higher,
more so in that direction.
Okay, let's use the bottom of the thing. As he climbs up, the torque increases. Therefore, the torque from the top has to also to keep it zero. So increase.
Wait, so
Yeah.
you're,
A.
you're outside of the waiver?
I know it's not.
Did you go there?
I think it's that reason.
Yeah, what's
There is friction though because of the roller.
The ladder is not
Like,
just because it has rollers.
I'll send him
No friction.
Oh yeah, Daisy's gonna go.
Wait, never mind. I don't know where to be now.
He's
All right, what do you say? Hey, why?
So the force on the wall is a torque. Force from the wall is a force on the wall from the ladder. And as the person ascends the ladder, the ladder ignoring the wall, the ladder wants to fall more so. Therefore, since the wall stops that, the wall has to exert more force. It has to exert more force to stop the fall.
What?
Emma. What?
I wonder why.
Go ahead.
Can we do that?
Hey man, Sam needs his keys.
Mhm.
What's
All right. So the net torque has to be zero. As the guy climbs, that provides more torque going this way. Clockwise, there needs to be additional increase of torque going counterclockwise from the wall. Okay.
Even Daniel Zhang could do that.
Okay, same scenario.
Oh, never mind.
Friction.
No, it's not.
I think you know what happens to friction.
Unless the guy weighs less as he climbs the ladder. Weighs more.
How much
Is this the same question?
He's
How
sweating,
fast was that though?
sweating very slow. You missed half the lesson.
That was so fast. I just.
No, actually, it's the
What was
next
the answer
day.
to the last one?
Yeah, today's Thursday.
Safe and serious.
Yeah, I know, it's like English.
No, it was increases. Okay,
Is
so
it torque
as the dude
increases?
climbs up, the torque increases. On the bottom point is the pivot. The ladder touches the ground at the pivot. So, so as he climbs up, the torque increases. So the torque from the wall has to increase as well.
Brad, you're right. The guy does lose mass. 'Cause as he works up, he sweats, and when the sweat gets
He doesn't.
he loses
Depending on
mass.
how out of shape he is, he sweats. If he starts.
Tell your neighbor.
We set the other thing as the pivot, and then as he climbs, the torque decreases. So the torque.
Oh, the ladder to the ground. I thought it was ladder to the wall.
You set the top point where the ladder and the wall are in contact, this is right? As the dude climbs, the torque decreases, so the torque from friction has to also decrease. It's the same question as the last
We set the
one.
point at the middle of.
So the torque friction goes
Decreases because the radius.
down,
My radius is
goes
zero.
down, and then torque from the ground.
So to keep it in
Goes
equilibrium,
right.
torque from friction.
Okay. It goes right.
Oh,
and it goes down. It looks like my computer
Not my problem.
like me to the computer and plug into the thing. Like I don't even know what it is.
Yeah,
Yeah, but it was like the gamer stuff is down, so it's like gamer stuff too.
Okay, correct answer is have a argument. This side versus that side. Not a fight, just an argument.
And for the ladder to not just move backwards.
Which means that there's gonna be.
I am gonna complain about your setting the pivot point at the bottom of the ladder because friction acts at the pivot, which means there's no torque from it.
Yeah.
Got it.
Why did
Which means it stays the same.
It means you just set it from the top.
No. Because we don't care about torque. What we care about is the movement
Carry
of
me
the
on
ladder.
that.
The ladder's not moving, therefore the net force is equal to zero.
She was
The force-
so hot.
force
Why'd
from
you
the
get
wall on the ladder increases, and therefore the force keeping it still has to increase, which friction is
That's a good idea. I like your point.
Yeah.
That's a good
I'm
point.
going with the data.
Agreed.
Oh.
Agreed.
Emma, you're weird.
Also, from a logical perspective, the higher you climb, the more likely it is to.
Yeah, exactly. That's also true.
Okay, correct answer is A. Okay. Here. All right. Okay. The,
That was why I was wrong.
oh dear.
Okay, so no one should say first.
All right. So as this guy climbs, this is going to increase. The easy way is to consider the sum of the forces in the x direction horizontally. As this increases, this is the only other horizontal force. So this has to increase to keep the total force in the x direction 0. Okay. To to address this being the pivot point, yes, this is as the guy climbs, the weight of the guy is decreasing the torque going in the counterclockwise direction. But this is not the only torque or friction is not the only force causing torque in the counterclockwise. Counterclockwise. Shoot, I didn't. Oh, yeah. They both cause torque in the same direction. This normal force is also changing, which provides torque. Okay. I know. I'm just trying to address the arguments that I heard.
Oh no, because it's static right now.
It should decrease.
What makes it decrease?
That's a good question. Hold on. Oh, because there's no friction. Shoot.
No, okay, I don't have a point here. It's just a question.
See, that's because
Yeah, really. This isn't really a thing.
Yeah. And also, there's so much context. Like, I set up a ladder so that if you don't have a person high up, the ladder will slip. Yeah, or I can set up a ladder so that if you have a person high up, it will slip.
I made it practice.
It's just kind of so like likelihood and like some like random events which are open up.
Oh, yeah, that's fine. Of all of the people who have set of all possible ladders.
Oh, you want the energy saving?
Wait a minute. That's probably an uncountable.
Oh no. Okay, you're right. It doesn't change. You're right. Normal force stays the same. As this is going, as this guy goes up, this causes the torque from the weight to decrease, and this increases to compensate. The normal force, the torque from the normal force stays the same.
Well, I just looked at it from a net force perspective.
Okay. Right. All right. Is everybody okay with higher on this one?
Yeah. It's just I don't like how you're defining likely because because for any given ladder, it's going to be with a person of a given weight, there's just going to be a point where it falls. So are you asking for us to calculate probability across the set of all ladders and all people? That's an uncountable. Those are uncountable sets.
All right.
Caroline, what were they called? This one's Reed. What's the other one? I think I just named him Chunky Boy. Really fat. Well, no, it's David. Oh wait, that's a sign. That's awesome. No, I just remember really.
That's a cool sign.
Owen's David now?
Middle name.
Or
Or at least this way says.
I would never lie.
I don't know
Anthony, a lot of people's name.
Daniel is your middle name Anthony?
No, it's Quinn. I can't pronounce that, so it might as well be Anthony.
You can't pronounce your middle name.
Boy, Brad can't.
I didn't know.
Brad, Quinn.
Daniel Quinzag.
What does it mean?
I'm gonna start calling you that.
Wait a minute,
No idea.
it's DQZ.
Yeah, I'm gonna say it's
Gary
actually
Quinn. No, it's actually K. You know this.
Oh, that's
I told you.
DK, Donkey Kong.
No, this is empty.
I'm
I
distracted.
keep trying to
I'm
focus
just-
on this.
I'm just-
I get a little farther in the question and then, oh, Donkey Kong.
He's just like that.
I got funnier when I moved here. Wow.
Vicious, man.
Yeah, you're.
Not like that.
You don't watch
Yeah, it's re-recorded.
Hi, Sam.
Screw you, Sam. Stop skipping school.
Sam, are you enjoying your belt these bites?
I can't read the question now.
That should be an easy question, right?
Yeah.
I agree. There are that one here.
I would. Well,
Can you read?
I mean, I would recommend drawing an extended free body diagram, but that's just a recommendation.
Imagine being able to visualize things in your brain. What are you, some non-aphrodisiac?
Yeah, actually, I am.
Oh my god. Sorry, my
I'm so jealous of
That's
you.
right.
Good reflex.
I'm so jealous of you, Brad.
About the answer.
Yeah, one freak out. No, you can't. No, you can't.
Donkey Kong.
No, I
Get you to go downstairs.
Do you guys have answers? You
Yes.
see?
Max, multiple choice. You just
Tell your neighbor. Tell them why you think so.
So it needs to be equal to the torque from the dinosaur. Yeah, pivot C. So the torque is W times L. And so that's got to be the vertical component of the
That's what I'm basing it on.
Because I'm not even.
Oh, yeah, that's right.
That's why he's on his computer. Because I do that all the time.
Therefore, that's.
Where's Calvin?
Calvin's asleep.
I'm known for not doing
He's still
work.
attached. He could be asleep.
There was a kid
Calvin, you should
a couple years ago who would always sleep in my class. I'm not going to say.
This guy.
And he asked me to write a letter of recommendation. I'm like, and one of the questions was on Common App. What words would you like? What words would you give to describe him? I was like, sleepy.
No way.
I did.
Did he get
Was he
accepted?
smart?
I didn't.
Yeah, like, that's
It was AP1 and APC. Slept through.
Did he get an
No.
Why did you take
I don't know. I mean, he was sort of smart, but not smart enough to sleep through every class.
Okay, so like me.
For a minute, I thought it was just shoes, but then. Well, actually, past the class. It's just Calvin. It's Calvin.
Yeah, no,
Sin would go on the. Yeah, but you're sorry.
You're not asleep here.
Calvin,
Because it's not first hour.
Calvin, you should like
Hey,
actually
what's
say.
it on the Bible?
All right.
I asked.
Correct answer is C. Okay, so your extended free body diagram looks like this. So if we make this the pivot, this component, it needs to have the same torque.
I don't know, I just was a poly picture in my head.
Okay. So
We were right up to the point about shrinking.
do what?
The little egg crank generator.
Yeah.
I love that how big a difference it makes when you do that.
Yeah.
Yeah, it's the one where you electrocute kids who got less than an A.
Nice when you mix up the it's really big.
Everyone
Still, that's what they did-
Satisfying.
That's what they did to me in second grade.
All right. Everybody good with that? I did. So the torque.
Hold on. I think the real question here, what do you buy at a dino store?
That's what I wanted.
Dino poop.
So the question is, what don't you buy?
Dinosaur cereal. Dinosaur food.
Yeah, so that's what I'm afraid of. Dinosaur poop and dinosaur themed cereal. I don't want dino O's. I want a dinosaur, damn. I want to ride a dinosaur to school every day.
Okay, well, you see these things called birds, they might work their fits well,
Jurassic Park.
All right, good. Okay, follow-up question.
I'm gonna pull that sound effect out once in a while. I actually understand all of this, so I'm not feeling that bad about it. What do you do?
Why are you looking at me like that?
I've been waiting for that realization.
But wouldn't the force be the same?
No, but like it's like on the
No,
hinge.
because look at your free body diagram, right? You've got weight
On
pulling
the
down,
rod,
tension
by the
pulling up, and then it's in, which means that
Which
it
is
provides no vertical.
yes.
Sorry, Kamai, this is my thing now. I spoil physics.
That's not what Sam would do.
No.
WWSC.
Sam, Jeff Alvina
What would Sam do?
Sam would be ranting about how he got a 73 on the multiple choice for 10 or something.
That's not 75.
What was it?
Okay, tell your neighbor, tell them why.
I already told all of my neighbors. Yeah.
Like a good neighbor.
Yeah, I think so, unless I was really short.
I think we should make the testing environment in physics the same as the testing environment in MBE, where we just talk to each other the whole time.
Bro, apparently I said Michael.
I can't
Like,
say
yeah, because like at the very end, she like did do like the last step. That was like the very really important step. That was like writing I equals to like yeah, I for IJK. So like what is there actually going to? So Michael, I got you. That's why I started with Calvin.
Gilmore was so chill about it. I went up and was like, hey Gilmore, did I forget a negative in this equation on my note card? And he was like, yeah, you did. I went and sat back down and took it was awesome.
Because like on the very last question, he didn't
I
remember
went up to Gilmore and said, is this right? He said, yeah.
That's like 1 or 2 points.
I went up to him on the
Why
one
did you
like
do
the
that?
sign
What did I
X,
say?
Y,
What did you
or
do?
X, Y question, and I was like, hey, is this okay to do? Because I know it's like easy calc stuff instead of.
Okay, correct answer is C. So if we were ranking them from least to greatest,
S tier is greatest.
tension would be the most because just the y component is equal to the weight. So overall it's going to be most, then weight. And because the y component is equal to the weight, there is no other forces needed in the y direction, the vertical direction. So this is 0 force vertically. Okay. So
No, why doesn't make sense? I think you caught my misreading.
So this is a question out of a civil engineering. Okay. It says determine the force on each member and truss and state if they're in tension or compression. Okay. So this is a question like this on steroids. You'd have to do an extended free body diagram of each member. Okay? So this is why they give 5 of these problems a week. It's just a lot of stuff. But there are some shortcuts. First one is called the method of joints. Okay? So they just in engineering they do English stuff. Well, I guess that's not English. Just kidding. A lot of times they'll have pounds. So they'll have a hinge on one side, a pin, and a roller on the other. Okay. So the first step in method of joints, they're going to recommend you labeling everything, so the joints and the members. Okay. And then what you're going to do is you're going to consider the whole thing, one whole truss system as one object, and do the extended free body diagram of the entire truss system. So you have the weight of the truss. Actually, this is a load, I think. Yeah. External load. And then you have the force from the pin, so the X component and the Y component, and then the normal force from the roller. Okay, so you set up those, the sum of the forces in the X and the Y direction, and the sum of the torques are equal to 0 based upon this whole thing. Okay, that's step 1. Typically, in any shortcut method, this is step 1. Draw the whole thing, draw the extended free body diagram of the entire truss system. Okay. Then the method of joints, here's where that comes into play. What you do is you just look at the joints, at the pins. Okay. And you're guessing whether these members are in tension or compression. Okay. One way that they teach you how to do it is like, just assume that all of them are in tension. Now, when you do this, you're like, well, that doesn't look like tension. This is the Newton's third law pair. The pin experiences a force this way if the member is being forced that way, if that makes sense. Okay. So you just make these forces parallel with each of the members here. And if you're wrong, the answer is going to be negative. And then you just know the force goes in the opposite direction. Okay. So you got here's pivot 1, point 1, here's joint 2, joint 3, and joint 4. Okay. The advantage of this is because you take them as points, you don't have torque. It's just the sum of the forces in the X and Y direction.
There's also the sum of forces in the Z direction, so we ignore that because, there are a total of 0 forces in the Z direction. So
correct.
So we're adding up a bunch of zeros. I think
you still have torque going on in the overall, like the overall system. But when you're looking at just the joints at the pins, that's it. So it's just a bunch of substitution, but it's way less than trying to do this extended free body diagram of each of those. Okay, so that's one shortcut method. Yeah, I remember doing this. This next one I don't remember doing. I don't think I ever did. This is method of sections. So anytime students come back, I'm like, hey, how can I make this class better? And this is one of the suggestions, like you got to teach a method of joins or sections. Like, what is it? So I look it up and learn it. So again, they're going to tell you to organize the label stuff. We don't really worry about the joints or the pins, but you got a roller on this side and you got a pin on the other. Okay. Step one again is draw the extended free body diagram of the entire truss system. Okay. And then what you're gonna do is you're gonna like play Fruit Ninja, and you're gonna slice the truss at a certain point. You're trying to cut as few members as possible.
That's back cut location. Yeah, you can make it to the F2 instead of 3.
Okay. Well, it depends on what you're trying to solve for. If we're trying to solve for E, you're going to be stuck cutting 3. Okay. Now, you could cut 4 if you want to. The cuts don't need to be a straight line. So you could like go.
So you can cut every single one if you want.
X to the 4th plus 3x squared.
But the point is you have 2 pieces now. Okay. And then you do extended free body diagram of 1 piece, possibly 2 pieces if that's helpful, but usually 1 piece will be sufficient. So you got extended free body diagram. These are always just going to put in tension, and if they turn out to be compression, then it'll end up being negative. Okay. So, blah, 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 blah. Label, yeah, nothing new there. And then do some of the forces in X and Y direction, some of the torques. And that should help you. Okay. So a lot of times when we are designing stuff, we want to know which member is going to experience the most tension or compression, and we design the bridge or the structure around that evaluation. Where if this is in, I'm looking at this, the D is going to be in compression. It's going to want a taco. Okay, so I want something that handles well under compression and not, I don't really care about the tension part of things. So this is going to be more concrete. F is going to be under tension and not so much compression. And so I want a material that can handle tension better than compression. So this is where the steel is going to come in. Okay. Some of these, depending on the load, might not experience much of anything. And so you can put something really weak. Does that make sense? Because you're all like engineering, you're all about cost analysis. I mean, the bottom line, like, can you save $1 and still be safe? Okay. So you don't want to reinforce something that doesn't need to be reinforced. Does that make sense? Okay. So those are 2 different shortcuts. Right, and extra weight. Okay. All right. Last thing is tipping or rolling over. Okay. So here, this car, if it does anything, it's going to start to slide or slip down the ramp. It's not going to roll over. Here, it's on the verge of slipping. How do I know? assuming this is the center of mass, the force of gravity, the line of action of the force of gravity goes right. We're going to call the pivot point the edge of that tire. It's about to tip when the force of gravity, the line of action of that, goes through that pivot point. Correct. Okay. And if you go beyond that, then this force of gravity is providing torque that's going to enable it to tip over. Good with that? Okay. All right.
So he's moving.
I'm moving. All right. So let's line these up nice and perfectly. Okay. And I'm going to start. Okay. So I'm going to slide this until it's just about to tip. How far was this going to go? Assuming this is uniformly dense, which is particle board. Pretty good assumption.
It should go about half.
It's about half. Does that look about half?
Yeah. The next one should go about
Okay. Now, what I'm going to do is I'm going to slide this next board. How far
I say about 30.
can I go? Okay, right there. It's teetering.
Yeah, that looks like a third.
Okay. So what this means is the location of the center of mass of this board assembly is right here. Does that make sense? Now, if I do the next board,
So now you get to about a 40. It's those things follow the Vermont numbers. Okay, if they're evenly dense, which I don't. But no, it doesn't look like a third. I'm not sure if it's a third. I think it's either like.
okay.
That's different.
Is this how they build bridges?
No.
Okay. I'm gonna pull this one back. It's making me a little bit nervous.
Okay, that's definitely not close to the line.
Okay.
So.
Good with that? If I do the next one, We're close. Whoa. Okay, that's close. Another one. Okay, now here's what I want you to see. That the top block board is completely off of the table. Go with that. So someone found this on the internet. Notice how many cards length.
Imagine how much time that would have taken.
Yes.
And then immediately fall over.
But how much time have you wasted in your lifetime?
Decent amount. You get further with just falling the harmonics. I don't know how many cards are.
Yep.
What's the limit?